Welcome back. In this video, we are going to solve problem 6-72, and that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbler. So statement is determine the absolute maximum bending stress in 1.5 inch diameter shaft, which is subjected to concentrated forces. The sleeve bearing at A and B only support vertical forces. So you can see this is the shaft, clear, and there are two concentrated forces, 400 and 300 pounds, and at A and B we have sleeve bearing which only exert vertical forces. So we'll find the absolute maximum bending stress. So let's start with the solution. First step is that if you remove this sleeve bearing at A, so you will be having a reaction force which is RA, and if you remove this sleeve bearing at B, you will be having a reaction force RB. So we will draw the free body diagram. The free body diagram is shown over here. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, first moment is this 400 into perpendicular distance is 12. This is producing clockwise moment, so it will be negative. So I will write it minus 400 into perpendicular distance is 12. The second moment about point A is this RB into perpendicular distance is 30 inch. And this is producing counterclockwise moment, so it will be positive. So I will write plus RB into 30. Clear? And the last moment that is produced due to 300 pound force and perpendicular distance is this total length, which is equal to 12 plus 18, 30, 45 inch, and that is producing clockwise, so it will be negative. So I will write minus 300 into 45 will be equal to 0. So from here you will get 30 RB will be equal to 400 multiplied by 12 plus 300 multiplied by 45. And when you calculate it, you will get this RB will be equal to 610 pounds. Okay. Now we'll find this RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is upward, minus this 400 pound force plus RB, which is 610, and minus 310 will be equal to 0. So what we will get is that this RA will be equal to 400 plus 310 minus 610. So when you calculate it, you will get this RA will be equal to 90 pounds. Now you have RA and RB, so we'll move toward drawing shear force and bending moment diagram, because we need the maximum bending moment to find out the maximum bending stress. So for that, I will take the vertical lines from end of this beam, clear. Similarly from here, you will also take and you will draw a horizontal line to show the length in inches. X will be in inch, and on y-axis we have shear force that we have in unit pounds. Okay, now we will take, let each division will be equal to 100, so it is 100, 200 and 300. You can take it as per your scale. So minus 100, minus 200 and minus 300. Yeah, so you can see that at point A we have RA which is equal to 90 pound. So your first point will be, let this is 90 pound. So your first point will be this one. Now moving from point A till 400 load, there is no other shear force, so it will remain horizontal till this point, and it will be a straight horizontal line. Yeah. Now at this point we have 400 downward, so 90 minus 400 will bring it to minus 310. So at this point it will change to 310. So let this point is 310 pounds. So shear force will change from 90 to 310. And again moving from this 400 pound till RB, there is no other shear force, so it will remain horizontal till point B, so it will remain horizontal till this point. Yeah. Now at point B we have RB which is upward, so minus 310 plus 610 will be equal to 300. So shear force will change to 300. This is minus 310 and this is 300. So shear force will change minus 300 to 300 pounds. And again moving from point B till end we have no other shear force, so it will remain horizontal, clear. And at the end you can see you have minus 300, that is downward, so it will cause the shear force to come to 0 point. So this is your shear force diagram. Now from this shear force diagram we will find the maximum bending moment. So again for that I will take a horizontal line to show length in inches, and on vertical axis we have moment that will be having unit pound into inch. So let each division is of 500, clear. So it will be 1000. Similarly minus 500, minus 1000, clear. So minus 2000, minus 3000, minus 4000, and this will be minus 5000. You can extend this vertical line, clear, and similarly from here as well. Okay, now the first area at point X we have X is equal to 0, so movement will be 0. So at first point we will having movement will be equal to 0. So this is your first point. Now the area under the shear force diagram is this area. This is the first area, and this area is equal to 90 multiplied by this length 12, and that will give you 1080. So at this length we have 1080, which will be just like here. So 1080, let this point is 1080 pound into inch. You can see that shear force is a horizontal line with 0 degrees, so bending moment will be 1 degree higher and slope will be increasing because this is a positive area. So we will join these 2 points, so it will be like a straight line. Clear? The second area is this area. You can see this shaded area, and this is rectangular, so its area will be equal to minus 310 into 18. So it will give you 5580. So plus 1080, and this is minus 5580 will give you minus 4500. So it will be somewhere here. 4500 will be somewhere here. Clear? So I will locate this point. This is 4000 minus 4500, and you can see that shear force is a horizontal line with 0 degree, and this area is negative. Clear? So bending moment will be 1 degree higher and slope will be increasing, so it will be a straight line like this. So I will join these 2 points using a straight line. Okay, now the third area is this area, and this area you can see is positive area, and this is equal to 300 multiplied by the length, which is 115 inch. And you can see this area will be equal to 4500 plus 4500. So minus 45 plus 45 will cause the bending moment to 0 at this point. And you can see you will get this straight line. Clear? Because this area is positive. Clear? This area is positive, and this shear force is a horizontal line with 0 degree, so bending moment will be 1 degree higher and slope will be increasing. So this will be your bending moment diagram. Okay, now from this bending moment diagram, from BMD, so we will get maximum absolute value of maximum bending moment. So from here you can see the maximum bending moment is minus 4500. We are taking the absolute value, so it is 4500 pounds into inch. And we know that maximum bending absolute value of bending stress is equal to maximum bending moment absolute into C divided by I. Since we have been given a shaft having diameter of 1.5 inch, so its radius C will be equal to C is equal to radius, and that C is equal to D divided by 2. So diameter was 1.5 inch divided by 2 will give you 0.75 inch. So C is there, and I moment of inertia, second moment of inertia for a shaft having radius C is equal to pi by 4 C power 4. So put the value pi by 4, and C is 0.75 power 4 will give you the moment of inertia. Now you have C, you have I, and you have M. So put it in this formula. Maximum absolute value of bending stress is equal to 4500 multiplied by C, which is 0.75 inch, divided by pi by 4 into 0.75 power 4. So when you solve this, it will be 13.6 into 10 to the power 6, 10 to the power 3 psi, pound per square inch. And when you convert it into KSI, so this maximum bending stress, absolute value of maximum bending stress, comes out to be 13.6 KSI, which is the answer of our this question. And that was all about this problem 6-72. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 6-73 that is taken from chapter number 6, bending, and book name is Mechanics of Material by R.C. Hibbler. So statement is determine the smallest allowable diameter of the shaft which is subjected to concentrated forces. The sleeve bearing at A and B supports only vertical forces, and the allowable bending stress is 22 KSI. So you can see this is the shaft, and there are two concentrated load 400 and 300 is applied at these points, and at A and B we have sleeve bearing that only exert vertical reaction forces. So allowable bending stress is given, so you have to find the smallest allowable diameter of the shaft. So let's start with the solution. So first step is that if you remove this bearing, sleeve bearing at point A, so you will be having reaction force RA, and similarly if you remove this bearing, so you will be having a reaction force RB, which is exerted by bearing on this shaft. So we'll find this RA and RB. The free body diagram is already shown over here, already drawn. So we will find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first moment will be this 400 into perpendicular distance is 12, and this is producing clockwise, so it will be negative. The second moment will be this RB, and now perpendicular distance is this 30 inch, and this is producing counterclockwise moment, so it will be positive. And third moment will be 300 into perpendicular distance is this 45 inch, and this is producing clockwise. So the sum of all the moment about point A must be equal to 0. So I will write minus 400 into 12 plus RB into 30 minus 300 into 45 will be equal to 0. So when you solve this, you will get this RB will be equal to 610 pounds. Now you have this RB, we can find RA by using equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA is upward minus 400 which is downward plus RB which is upward and that is 610 minus 300 pounds is equal to 0. So from here RA is RA minus 90 is equal to 0. So RA will be equal to 90 pounds. Now you have RA and RB, so we will draw the shear force and bending moment diagram. Why we draw it? Because we have allowable bending stress. So we know that allowable bending stress is maximum bending moment into C divided by I. So we will need bending moment diagram in order to find the maximum bending moment. So what we will do is we will take vertical line from the end of this beam and first we will draw the shear force. So here we will take horizontal line to show X in inches. And on Y-axis we have shear force that will be in unit will be in pound. Okay. So let one division is equal to, you can see one division is of 100. So this will be minus 100, minus 200, minus 300. Okay. So at this point A, we have RA. So RA is 90 pounds. So your first point will be, let this is your 90 pound, this point. Now moving from point A till point of 400 pounds, there is no other shear force. It will remain horizontal. Clear? So now this 90 will be horizontal till this point. Now at this point we have 400 downward, so 90 minus 400 will cause it to change it to minus 310. So shear force will change to minus 310 and it will be downward. So let this point is minus 310 pounds, so it will change to downward. Now again going from this point till this point, there is no other shear force, so it will remain horizontal till this point and we will get a horizontal line. This is minus 310. Now at point B we have RB which is upward, so minus 300 plus RB is 610 will cause it to go to 300 pounds. So at this point shear force will change to 300 pounds. So this is 100, 200. So this will be 300. So this is the point, not this. It will be like here, this point. So at this point it will be 300 pounds. So shear force will change from minus 310 to 300. Now moving from B till end, there is no other shear force. So it will also remain horizontal line. And at the end you can see minus 300, that is downward, will cause it to 0. Clear? So this is your shear force diagram. Now with the help of this shear force diagram, we will draw the bending moment diagram. For that I will draw a horizontal line to show the length X in inch, and on Y-axis we will have moment that will be having unit pound into inch. Let each division is 1,000. You can choose as per your scale. 2,000. Similarly minus 1,000, minus 2,000, minus 3,000, and minus 4,000, and minus 5,000. Okay. So at point A, at origin, we have moment will be equal to 0 because X is equal to 0. Now the area under the shear force diagram will give you bending moment. So this is the first area, that this is A1, and this area is equal to 90, which is the height, and this length, which is 12. Clear? So when you multiply it, it will give you 1080. So at this length, we have moment 1080. So it will be somewhere here. So let this point is 1080. Now you can see shear force is a horizontal line with 0 degree and this area is positive. So bending moment will be 1 degree higher. It will be a linear straight line and the slope will be increasing. So we will join these 2 points. Okay, this is the point, not this point. This will be the point. Let me correct it. Let this point is 1080. So this is the first point. Now the second area is this area, and this area is, let this area is A2, and this A2 is equal to this length, which is minus 310 into width 18. So this will give you minus 5580. Clear? So moment at this length will be equal to 1080 plus minus 5580 will cause it to minus 4500, and this will be somewhere here. Clear? So we will first locate this point. So this point, this is minus 5000. So this point will be somewhere here. So it is minus 4500. Now you can see shear force is a horizontal line and this area is negative. So bending moment will be 1 degree higher, but its slope will be decreasing. It will be a straight line. So we'll join these 2 points using straight line. And the last area is this A3, and this A3 is equal to 300 multiplied by this width, which is 15 inch, and that is equal to 4500. So at this point, the moment will be minus 4500 plus 4500 will cause it to 0. So this will be the moment. Now you can see that shear force is a horizontal line and this area is positive. So bending moment will be 1 degree higher and slope will be increasing, and it will be a straight line, linear line of 1 degree. So this is your bending moment diagram, BMD. Now you can see from this BMD, we have maximum absolute value of bending moment is equal to minus 4500, and unit will be pound into inch, which will give you maximum bending moment. Absolute value of maximum bending moment is 4500 pounds into inch. We know that maximum bending allowable bending stress is equal to maximum bending moment into C divided by I. So we have a circular shaft having diameter D, so its radius will be equal to C. So diameter is equal to 2 times C. Okay, so we are going to find the radius and then we will convert it into C. And I is the moment of inertia, and moment of inertia for circular shaft having radius is equal to pi by 4 C power 4, where C is equal to radius. Clear? So you can put the value sigma allowable bending stress is given as 22 ksi. So we will write it 22 ksi. So 22 into 10 to the power 3 will be equal to 22 into 10 to the power 3 psi, pound per square inch. Maximum bending moment is 4500 pound into inch, and C is there divided by pi by 4 C power 4. So from here you will get this one C will cut with this, so we will be having C3. So I will write C3 is equal to 4500 divided by pi by 4 multiplied by 22 into 10 to the power 3. And when you take the cubic root on both sides using your calculator, so you will get this C will be equal to 0.639 inch. Now you will need the diameter. So diameter, you know that diameter is equal to 2 times of radius, which is C. So I will write 2 multiplied by 0.639 inch, and this diameter D will be equal to 1.28 inch. And which is the answer of this question? And that was diameter D of this shaft for the allowable bending stress and for the given loading shown. That was all about this problem 6-73. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-75. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by R.C. Hibbler. So statement is the shaft is supported by smooth thrust bearing at A and smooth journal bearing at D. If the shaft has cross section shown, you can see the shaft cross section. The outer radius is 40 millimeter and inner radius is 25 millimeter. Determine the absolute maximum bending stress in the shaft. So this is the shaft. At A we have a smooth journal thrust bearing. At D we have smooth journal bearing. At B and C we have a 3 kilonewton load that is downward. The length is shown over here. The total length is 3 meter. Clear? So you have to find the absolute maximum bending stress in the shaft. So let's start with the solution. So first step is that if you remove this smooth thrust bearing, so you will be having reaction force exerted by this bearing on the shaft, which is equal to RA. And if you remove this smooth journal bearing at D, so it will apply a reaction force RD on the shaft. So you'll find this RA and RD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, the first moment will be this 3 kilonewton load and perpendicular distance is 0.75. It is clockwise, so it will be negative. So I will write minus 3 into 0.75. The second moment will be due to this 3 kilonewton load, and now perpendicular distance is this one, which is 0.75 plus 1.5, and that is 2.25, and it is also clockwise, so it will be negative. So I will write minus 3 into 2.25 meter. And the last moment that is produced due to this RD and perpendicular distance is this total is 3, and this is producing clockwise, counterclockwise, so it will be positive, plus RD into 3. And the sum of all this moment about point A must be equal to 0. So when you calculate it, you will get this 3RD will be equal to 9, and from here you will get this RD will be equal to 3 kilonewton. Okay, now you have this RD, so you can find this RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is upward, so RA minus this 3 kilonewton and minus this 3, so minus 3 plus RD, which is plus 3, is equal to 0. So from here this will cancel with this, so RA will also equal to 3 kilonewton. Now we have RA and RB, so we will move toward finding the shear force and bending moment diagram, because we have to find the maximum bending moment and maximum bending stress, and that maximum bending stress is maximum bending moment into C divided by I. So here the hollow circular shaft, so it will be outer radius. So for finding a maximum bending moment, we will draw the shear force and bending moment diagram. So again, for that I will take the horizontal vertical line from the end of this beam, clear, and then horizontal line to show the length in X in meter. On y-axis we will have shear force that will having unit kilonewton. Let each division is 1.5 kilonewton, so this is 3. Similarly minus 1.5, you can choose as per your required scale or chosen scale. Now you can see that first at RA we have, at point A we have RA, which is 3 kilonewton. So your first point will be this one. Now moving from point A till point B, there is no other shear force, so till this point B this shear force will remain horizontal. Okay, now at this point B we have minus 3, that is downward. So plus 3 minus 3 will bring it to 0. So shear force will change from 3 to 0. Now again from B to C there is no other shear force, so it will remain similar horizontal line till point C. So this is your point C, this is your point B, this is C. So this shear force remain horizontal. Again at point C you have -3 downwards, so 0 minus 3 will be equal to -3. So shear force will change it here and it will be -3. And moving from C to D there is no other shear force, so it will remain same horizontal line. Clear? And at the end you can see you have RD which is +3. So -3 plus 3 will bring it to 0. Okay, so this is your shear force diagram, SFD, shear force diagram. Now we'll find the bending moment diagram. For that I will draw a horizontal line again to show the length of beam, and this length will be in meter. And on y-axis you have moment that will have unit kilonewton into meter. So let one division is 1 kilonewton into meter. This is 2, this is 3. Similarly -1 -2. So at x is equal to 0 we have moment is equal to 0. Now the first area under the shear force diagram is this area, and this area is this height which is 3, and this length is 0.75. So 3 into 0.75 will be equal to 2.25. So at this point we will have 2.75. So first we'll look at 2.25, sorry. So let this point is 2.25. Now you can see that shear force is a horizontal line with this area is positive and this is 0 degree line. So bending moment will be 1 degree higher, it will be a linear line, and slope will be increasing. So you will join these 2 points using straight line. Now here in this region there's shear force is 0, so bending moment will remain constant till this point. So it will be a straight line till this point. This will be 2.25. Now the area under the shear, this area under this shear force diagram is -3 into 0.75, which is equal to -2.25. So plus 2.25 minus 2.25 will bring it to 0 at this point. Clear? So your new point, bending moment at this point will be 0. And you can see that shear force is a horizontal line with this area is negative, so bending moment will be a linear line and slope will be decreasing. So we'll join these 2 points using a straight line, and that will be your BMD, bending moment diagram. Okay, now from BMD, bending moment diagram, you have bending moment, maximum absolute value of bending moment is equal to 2.25, and unit will be kilonewton into meter. Clear? So this will be the maximum bending moment, will be 2.25 kilonewton into meter. So we have been given that hollow circular shaft, outer and inner radius are given, that is outer is 0.04 and inner is 0.025 meter. So I for circular second moment of inertia of circular shaft is pi by 4 into C outer power 4 minus C inner power 4, where C is the radius. So you can just put the value pi by 4. C outer was 0.04 power 4 minus C inner is 0.025 power 4. Clear? And what about C outer? C outer is the maximum distance from the neutral axis. So you can have all now you have all the values. So you can just put it in this formula that maximum bending stress is equal to maximum bending moment and C outer divided by I. So maximum bending moment is 2.25 kilonewton. So 2.25 into 10 to the power 3 will be Newton into meter, and C outer is 0.04 divided by I, which is pi by 4 into 0.04 power 4 minus 0.025 power 4. So again, when you calculate it, you will get 52.8 into 10 to the power 6 Pascal. And when you convert it into megapascal, so maximum bending stress will be equal to 52.8 megapascal, which is the answer of this question. So maximum bending stress for the loading and the hollow circular shaft is calculated is 52.8. That was all about this problem 6-75. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-82 that is taken from chapter number 6, bending, and book name is Mechanics of Materials by R.C. Hibbler. So statement is the shaft is supported by smooth thrust bearing at A and smooth journal bearing at C. If diameter is 3 inch, determine the absolute maximum bending stress in the shaft. So you can see this is the shaft having diameter 3 inch, and at point A we have smooth thrust bearing, and at point C we have smooth journal bearing. At B and D we have a load of 3600 pound and 1800 pound. So you have to determine the absolute bending stress in the shaft. So we know that this maximum bending stress in the shaft is equal to maximum absolute value of maximum bending moment into C, which is distance from neutral axis to the outermost, and that is radius, divided by I. So we'll find this maximum bending moment by using shear force and maximum bending moment diagram. So let's start with the solution. What will be the first step is that if you remove this smooth thrust bearing at point A, so you will be having a reaction force which is represented as RA, and if you remove this smooth general bearing at point C. So you will be having a reaction force at C, which is RC exerted by this bearing on the shaft. So we'll find this RA and RC by using equation of equilibrium. So first equation of equilibrium is that sum of all movement about point C must be equal to 0 and taking the counterclockwise movement as positive. So about point C, the first movement will be this RA into perpendicular distance is 6 feet, and that is producing clockwise movement, so it will be negative. So I will write it RA into 6, and that will be minus. The second moment will be this 3,600 pound force, and perpendicular distance is 3 feet, and this is producing counterclockwise movement, so it will be positive. So plus 3600 multiplied by 3, and the last moment will be due to this 1800 pound, and perpendicular distance is 3 feet, and this is also producing clockwise, so it will be negative. So I will write minus 1800 multiplied by 3 is equal to 0. So from here we will get 6RA will be equal to 5,400 pounds, and from here you will get RA is equal to 900 pounds. So you have this RA, we will find this RC by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA plus RC minus 3,600 minus 1800 will be equal to 0. So RA minus 3,600 plus RC, which is 900 minus 1800, is equal to 0. So from here you will get this this RC is not known. This 900 is RA. So 900 is RA and RC is not known. You can see RA is 900 minus 3600 plus RC plus 1800. So you will get this RC will be equal to 4,500 pounds. Now you have this reaction force, so we'll move toward shear force and bending moment diagram. So for that, I will draw the vertical line from the end of this beam. Clear? And first we will draw a horizontal line to show the length in feet. X will be in feet. On y-axis we have shear force, that will be in, the unit will be pound. So let each division is of, you can take it, let for example this is 1000 pound, 2000 pound, similarly minus 1000 pound, minus 2000 pound, minus 3000 pound. You can select as per your own scale. So at point A we have RA, which is equal to 900. So first point will be 900. So now let 900 is this point. This is 900. Now moving from point A to B, there is no other shear force, so it will remain horizontal till point B. So let this is, it will be horizontal line till point B, which is 900. At point B we have minus 3,600. So 900 minus 3,600 will bring it to minus 2,700. So shear force will change to minus 2,700. So 2,000, let's say this is minus 2,700 pounds. So shear force will change from 900 to minus 2,700. Now moving from point B to C, there is no other shear force, so it will remain horizontal. Clear? So this minus 2,700 will remain same over there. Now at C we have RC, so minus 2,700, and RC is 4,500. That will give you 1,800 pound force. So shear force will change from this to 1,800. So let this is your 1,800. Shear force will change from minus 2,700 to 1,800. And from C to D, there is no other shear force, that will remain same. And at the end, we have minus 1,800, which will bring it to 0. So this will be your shear force diagram. Now we will find bending moment diagram. So again, for that, I will draw a horizontal line to show the length X in feet. And on Y-axis, we will having movement, that will be having Newton pounds into feet. Let each division is 1,500. Clear? So we will take this is 1,500 pound into feet. This is 3,000. Similarly, minus 1,500, minus 3,000, minus 4,500, and minus 6,000. At point A, we have shear movement is equal to 0 because X is equal to 0. So this is 0. Now the first area under the shear force diagram is this area, and this area is equal to 900, which is height, and the width is 3 feet. So 900 into 3 is 2,700. So your first point is 2,700. So we look at first point 2,700. So this is 1,500 and this is 3,000. Let's say this is 2,700 pounds into feet. You can see the shear force is a horizontal line with 0 degree, and this area is positive. So bending moment will be 1 degree higher. It will be a linear line, and slope will be increasing. The second area under the shear force diagram is this area, and you can see this height is minus 2,700 and width is 3 feet. So it will give you minus 8,100. So 2,700 plus minus 8,100 will give you minus 5,400 at this point. Clear? So we'll look at minus 5,400. So let, for example, this is the point where we have minus 5,400. Now you can see shear force is a horizontal line with this area is negative. So bending moment will be 1 degree higher and slope will be decreasing. So it will be a linear line. The third area under the shear force diagram is this area, and this area will be equal to 1800, which is this height, and this width is 3 feet. So that will give you 5400. So at this point, we have moment 5000 minus 5400 plus 5400 will be equal to 0. So you can see that shear force is a horizontal line with this area positive. So bending moment will be 1 degree higher and slope will be increasing. And you will join these 2 points using a linear line. Clear? So this will be your BMD, which is bending moment diagram. Now we will use this formula that maximum bending stress is equal to maximum bending moment. So from BMD, the maximum absolute value of bending stress, the bending moment will be equal to, you can see this is minus 5400 pounds into feet. Clear? And we will get 5400 absolute value will be positive feet, so it will be maximum bending moment absolute value. And if you want to convert this feet into inch, so we know that 1 feet is equal to 12 inch. Clear? So 5400 multiplied by 12 will give you unit pounds into inch. Clear? Now we have solid diameter D is given as 3 inch, so radius we have written as 1.5 inch. So C is equal to 1.5 inch, and we will need I, second moment of inertia. So second moment of inertia for solid circular shaft having radius C is pi by 4 C power 4. So pi by 4 into 1.5 power 4. Now you have all these values, so put it in this formula. So you will get maximum absolute value of bending stress is equal to maximum bending moment absolute into C divided by I. So maximum bending moment is 5400 multiplied by 12, and C is 1.5 divided by I is pi by 4, 1.5 power 4. Clear? So when you calculate it, you will get maximum bending moments comes out to be 24.4 into 10 raised to power 3 psi, or you can see that maximum bending stress is 24.4 KSI, kilo pound per square inch, and which is the answer of this question. And that was all about this problem 8-6-82. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-83 that is taken from chapter number 6, bending, and book name is Mechanics of Material by R.C. Hibbler. So statement is the shaft is supported by smooth thrust bearing at A and smooth general bearing at C. If material has an allowable bending stress is 24 KSI, determine the required minimum diameter of shaft to the nearest 1/16 inch. So you can see this is the shaft that is having diameter D, clear, and at A we have a smooth thrust bearing, and at C we have a smooth general bearing. At B we have a load of 3600 pound, and at D we have a load of 1800 pound. So for the material, allowable bending stress is 24 KSI, so you have to determine the smallest diameter D to the nearest 1/16 inch. So let's start with the solution. So we know that allowable or maximum bending moment, bending stress is equal to maximum bending moment into C, which is the radius of this shaft, divided by I. So we know that for I, for this shaft having radius C, where C is equal to radius, diameter is given and C is radius, and this C is equal to D divided by 2. So for circular shaft having radius C is I is equal to pi by 4 C power 4. So when you put it in this formula, so allowable bending stress is equal to maximum bending moment into C divided by pi by 4 C power 4. So from here you will get C3 will be equal to maximum bending moment, clear, maximum bending moment into 4 divided by pi into allowable bending stress, and this C will be equal to, radius will be equal to cubic root of maximum bending moment into 4 divided by pi into allowable bending stress. So once we will find C, so we can find the diameter. Now you can see here C will require the maximum bending moment, clear, and allowable is given. So we will find this maximum bending moment by using shear force and bending moment diagram. For that, first step is that if you remove this smooth thrust bearing at A, so you will be having a reaction force RA by the bearing on this shaft. Similarly, if you remove this smooth general bearing at C, so you'll be having a reaction force RC by this bearing on this shaft. So we'll find this RA and RC by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point C is equal to 0, and taking the counterclockwise moment as positive. So about point C, first moment is this RA into perpendicular distance is 6. This is clockwise, so it will be negative. So I will write minus 6 times RA. The second moment will be this 3600 into perpendicular distance is 3, and this is counterclockwise, so it will be positive. So I will write 3600 into 3, and the last moment is due to this 1800 and perpendicular distance is 3, and this is clockwise, so it will be negative. So minus 1800 into 3 is equal to 0. So when you solve this, you will get 6 RA will be equal to 5400 and RA will be equal to 900 pounds. Now you have this RA, so you can find this RC by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is plus 900 because it is upward, minus 3600 plus RC, which is not known, minus 1800 will be equal to 0. So from here you will get RC will be equal to 4500 pounds. Now you have RA and RC, so you can find the shear force and bending moment diagram. You can draw it. So for that I will take the vertical line from the end of this beam and a horizontal line to show the length, which is in feet. X is in feet. We have V on Y axis having unit pound here. So let each division is 500 pounds. So 500 are 1000. Similarly, minus 500, this will be minus 1500. This will be equal to minus 2500 pounds. This will be minus 1000, minus 2000, etc. Yeah. Now we'll plot first point, and the first point is at point RA. We have RA, which is 900. So your first point will be 900. So 900, let 900 is this point. Now moving from point A till point B, there is no other force, shear force, it will be 900. But at point B, we have load of minus 3600. So it will change to minus 2700 at point B. So shear force will change to minus 2700. So let 2700 is this one, minus 2700. So shear force will change from this to this. Now moving from point B to C, there is no other shear force, so it will remain horizontal. But at point C, we have RC, which is 4500. So minus 2700 plus 4500 will give you 1800 plus value. So we'll locate 1800. So let 1800 will be somewhere here, because this will be 1500 and this will be 2000 pound. So shear force will change from minus 2700 to 1800. Clear? And moving from C to T, there is no other shear force, it will remain horizontal, and at the end you can see minus 1800 downward will cause it to 0. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for that, again I have to draw a horizontal line to show X in feet, and on Y axis we have a bending moment that will be unit pound into feet. Let one division is 1500. So 1500, this will be 3000. Similarly, minus 1500, minus 3000, minus 4500, and minus 6000. Here, and at X is equal to 0, we have moment will be equal to 0. Now first area under the shear force diagram is this area, and this area is equal to 900 multiplied by this length, which is 3 feet. So that will be equal to 2700. So first point at this we will have 2700. So let 2700 is this one. Now you can see shear force is a horizontal line with 0 degree. So bending, and this area is positive. So bending moment will be 1 degree higher. It will be a linear line, and slope will be increasing. So we'll join these 2 points. The second area is this area, and this area is equal to minus 2700 multiplied by 3 feet, and that will be equal to 8,000 minus 8,100. So plus 2700 minus 8,100 will be equal to minus 5,400 at this point. So we'll locate minus 4,500. For example, if this is the point, minus 5,400. Now you can see shear force is a horizontal line, and this area is negative. So bending moment will be a linear line, and slope will be decreasing. So we'll join these 2 points using straight line. The third area is this area, and this area is equal to 1800 multiplied by this length is 3 feet. So that is equal to plus 1500. So minus 1500 plus 1500 will bring to 0 at this point. Clear? So this will be your next point. Now shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher, and slope will be increasing because area under the shear force is a positive area. So this is your bending moment diagram. Now from this BMD, clear, this BMD, we have maximum absolute value of bending moment is equal to minus 4,500 pounds into feet. So this maximum bending moment is equal to 5,400 pounds into feet, and we want to convert it into pound into inch. So 1 feet is equal to 12 inch. So I will multiply it with 12, and unit will be pounds into inch. That will be the maximum absolute value of bending moment. Now put it in this formula. So we will get C is equal to maximum bending moment, which is 5,400 multiplied by 12 into this formula. We have 4 divided by pi into allowable bending stress is 24 KSI. So I will write 24 into 10 to the power 3. That will be PSI, pound per square inch. And we will have a cubic under root. So when you solve this, clearly you will solve this. So you will get C, and that C will be equal to 1.51 inch. So we need diameter. So diameter is equal to 2 times radius. So 2 multiplied by 1.5, 1.51 will bring it to 3.02 inch. Now you have diameter is equal to 3.02 inch there, and we have been given to calculate the minimum diameter nearest to 1 over 16. So 3 inch is 3 plus 0.02 inch. So 1 over 16, we know that 1 over 16 is equal to 0.0625, which is greater than this value. So, but we have been asked nearest to 1 over 16 inch. It's clear? So we will choose the diameter D is equal to 1 by 16 inch. And this is the answer of our this question. So 3 into 1 by 16 inch diameter is selected or calculated for this shaft under the given loading and for allowable bending stress of 24 ksi. And that was all about this problem 6-83. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me.